So, screen is visible.
Yes, sir.
Yes, sir.
Okay. Now, what type of problems you have solved earlier? What type of problems you have solved? So, there you have solved the component which is subjected to only one type of stress, or it is subjected to two type of stress in fatigue stress analysis.
One type of stress.
Only one type of stress, right? Okay. Suppose if a component is subjected to two fluctuating loads, if a component is subjected to two fluctuating loads, so then you need to analyze that one with the help of combined loading. Okay. So, combine means what? Combine means what? Adding up, is it right? Adding up or other meaning? Combine.
Adding up.
Adding up. Okay. So, now in this case, if a component is subjected to fluctuating bending stress and fluctuating shear stress, how you need to analyze it? Okay. Suppose if a component is subjected to the fluctuating axial stress and fluctuating bending stress, how you can analyze? Next, if a component is subjected to, if a component subjected to, so fluctuating axial load and fluctuating shear load, so how we can analyze it? Okay. So, to find out the dimensions or to find out the stress, what is what the allowable stress or design stress. Okay. So, we need to go for the conversion of the equations. So, what you have noted for the Soderberg relation as well as the Goodman relation. Okay. So, now you need to convert those values into equivalent amount of stress here, equivalent amount of stress. Okay. Suppose if it is suppose if it is made of brittle material, so then you need to go for the Goodman relation. If the material is made of ductile material, so then you need to go for the what Soderberg relations. Okay. So, let us go through the data handbook. Okay. Let us go through the data handbook. So, now we will just open the data handbook here. So, here, okay, suppose the equivalent maximum shear stress and normal stress when it is subjected to the fluctuating loads, either it may be normal stress, that is what, either it may be normal stress or either it may be bending stress. Okay. Similarly, it is what equivalent shear stress. Now, equation is 2.22a and 2.22b. Okay. Now, once you got the value of equivalent normal stress, okay, so and the equivalent shear stress, then you can find out either the maximum stress or either the dimensions with the help of these two equations. That is what equation number 2.23a by using maximum shear stress theory, okay, and equation number 2.23b is what using maximum normal stress theory, right. So, now how to find out the value of tau eq and tau sigma en. Okay. So, it all depends on the again calculation of the mean stress as well as calculation of amplitude stress, right. So, now how you got here, I will just give here. You already noted, let us go for the equivalent normal stress there. How you got the equivalent normal stress? Okay, let us just go for equivalent normal stress. So what they have written equation, sigma eqn equal to, okay, sigma m plus kf into sigma a divided by a b c into sigma en, right. Okay, so we just cross check equation here. Now sigma 1, okay, so sigma yp is here, okay, sigma m plus sigma yp divided by sigma en ktf sigma a divided by abc. We left sigma y here, right. Now it's what, sigma y. So what is the equation here? Let us consider based on Soderberg relation. Soderberg relation. So what it is, 1 by n equal to, okay, so 1 by n equal to, so kf into sigma a divided by, okay, I will write equation according to now kf into sigma a divided by a b c into sigma en, okay, plus sigma m divided by sigma y, okay. Now let us take this as an FOS here, and is what it is, a FOS, factor of safety. Now if you divide, if you multiply above equation, okay, with sigma y, okay, or sigma yp on both sides, okay, on both sides. So what will get, if you multiply the equation with sigma yp on both sides, now this is what a sigma y by n equal to, okay, so kf into sigma a into sigma y, okay, so divided by a b c into sigma en plus sigma m into sigma y divided by sigma y. Now so sigma y by n is what, it is allowable stress, okay, it is what, allowable stress, okay. So now we can use in this case as it is equivalent normal stress, equivalent normal stress. So sigma y by n, okay, so I'll go for, so equivalent normal stress, okay. Now so this is equal to, now kf into sigma a divided by a b c, right, okay. Now sigma y by sigma en, right, plus sigma m, okay. So now this equation has rewritten here, okay? This equation has rewritten. You got how the equation, you got equivalent normal stress and equivalent normal shear stress, okay. So similarly the equivalent normal shear stress, sorry, equivalent shear stress, so what it is, 1 by n equal to kf into tau a divided by a b c into tau en, okay, plus tau m divided by tau y. Again if you multiply both sides with tau y, okay, with tau y. So, what will get here? So, tau y divided by n equal to kf into tau a divided by ABC into tau en into tau y plus tau m into tau y divided by tau y. Now, in this case you are going to get cancel here. So, tau y get cancels here. So, now tau y by n. So, it is what allowable stress or permissible stress. Now, in this case you consider it as a equivalent shear stress, that is what tau eq. So, now tau eq equal to, so now I will arrange the terms here, tau m kf divided by tau a divided by ABC tau y divided by tau en. Okay. So, I think this is equation number 2.23b. We'll check it. Equation number 2.22b, right? Equation number 2.22b. Earlier one, equation number 2.22a. So, now this equation is 2.22a, right? Now, how to get the dimensions or how to calculate the maximum shear stress? So, then you go for using the maximum normal stress theory, maximum normal stress theory, okay, or the maximum shear stress theory. Right. So, now in this case let us go for sigma max equal to, okay, according to maximum normal stress theory, sigma max equal to sigma eq plus, okay. So, it is I think divided by 2 is there, okay. So, divided by 2 plus 1 by 2 square root of sigma eq square, okay, plus 4 tau eq square, okay, right. Now, similarly according to maximum shear stress theory, according to maximum shear stress theory, tau max equal to 1 by 2 in bracket sigma eq square plus 4 tau eq square, right. So, now you can find out dimensions or the maximum load if you know the material and its property. If you have the dimensions and load, you can find out what is the maximum stress it can sustain. Maximum stress it can sustain, right? You got? Is clear?
Yes, sir.
Okay. Now, you go for problems here. Okay, you note down. A cold drawn steel rod of a circular cross section is subjected to a variable bending moment, okay, variable bending moment of 540 Newton meter, okay, to 1080 Newton meter. Okay. As the axial load varies, axial load varies from 4 kilonewton to 10 kilonewton. Full point. Next, the maximum axial load, the maximum axial load and maximum bending moment occur at the same instance. At the same instant. Full point. Okay. So, the material has an ultimate stress of 570 megapascal and yield stress of 420 megapascal. Full point. Taking factor of safety of 2, determine the diameter of the rod. Okay. So, now this is what the given problem. Okay. So, here it is what, it is a cold round steel rod, circular cross section, okay, is subjected to a variable bending moment, okay, and variable axial load. Is subjected to variable bending moment and variable axial load. Okay. So, first you note down all given data. First you note down all given data. Okay. Right. So, minimum bending moment, okay. So, let us go for this as a M minimum. How much it is? 540 Newton meter. Okay. So, next maximum bending moment, it is what, M max, this is 1080 Newton meter. Okay. 1080 Newton meter. Next, now the minimum axial load, it is F minimum, this is 4 kilonewton, okay, and the maximum axial load F max equal to 10 kilonewton. Okay. Now, so sigma u is given. Okay. Sigma u is 570 megapascal. Okay. Sigma y is given, it is 420 megapascal. Okay. And FOS is given, it is a 2, FOS it is a 2, right. So now other parameters are not specified here, other parameters are not specified. Now, so if I draw the diagram, for this problem, so it is subjected to axial loads, okay. One is minimum, one is maximum. It is also subjected to bending moments here, okay. So minimum bending moment and maximum bending moment, okay. And also they have given a condition here. Condition is that when maximum bending moment occurs, at the same time maximum tensile stress occurs, okay. When the minimum bending moment occurs, similarly at the same time minimum axial load occurs, okay. This is what given. So now let us find out first consideration of bending moment, okay. So I will go for a solution here. So let us first consider bending, right. So first, what is the maximum bending stress? What is the maximum bending stress? So what is the maximum bending stress here? Sigma B max equal to, so M max divided by Z, okay. So M max is, it is 1080 into 10 to the power of 3 Newton mm here, divided by pi dq 32, okay. So now this is what, 32 into 1080 into 10 to the power of 3 divided by pi dq, right. Now similarly calculate minimum bending stress. Minimum bending stress. So now this is what M minimum divided by Z. So 540 into 10 to the power of 3 divided by pi dq 32. So how much you will get? 32 into 540 into 10 to the power of 3 divided by pi dq. Okay. Next we calculate what is the mean bending stress or average bending stress, okay. So sigma min equal to sigma m equal to sigma max sigma minimum divided by 2, right. Next we can calculate the amplitude stress, okay, or the variable stress. So now this is what sigma A equal to sigma max minus sigma minimum divided by 2, okay. So you please calculate and give the value. So what is the sigma m? Rule number 26. Rule number 26. What is the sigma m? Rule number 27.
Yes, sir.
What is the sigma m? ಎಷ್ಟು sigma m you will get in terms of pi d cube, or you can write in terms of d cube.
So 8.25 into 10 raised to 6 by d.
How much?
8.25 into 10 raised to 6 divided by d cube.
8.25 into 10 to the power of 6 divided by d cube, right? This is sigma m.
Yes.
Next, what is the sigma a?
2.75 into 10 raised to 6.
2.75 into 10 to the power of
6.
Okay. Now, as you got a both value, so now you calculate. So, what is the equivalent stress due to bending? Equivalent stress due to bending, right? Okay. Now, equivalent stress due to bending. Okay. So, you refer design data handbook, note down equation number 2.22a. Okay. So, now sigma eqn equal to, okay. So, note down equation from data handbook. Okay. So, sigma eqn equal to sigma m plus sigma y by sigma en, right. Next, this is what k of sigma a divided by a b c, divided by a b c. So, you look out the parameters here which are not there. Okay. Now, sigma m you have calculated, okay. Sigma y you have calculated, sigma a you have calculated. So, now unknown value is here, it is a kf, okay. Sigma en is unknown value, a is unknown value, b is unknown value, and c is unknown value, right. Now, in this case you need to write clearly assuming. Okay. So, now as this is a case of the bending, okay, as is a case of bending. So, let us consider load factor as a 1. Okay. Now, in this case you need to assume all the parameters here. If they are not specified, you must assume. Okay. Now, as it is a circular rod, let us go for fatigue stress concentration factor equal to 1. Okay. Fatigue stress concentration factor equal to 1. So, we can take the value of surface factor as well as size factor from a range 0.8 to 0.95. Okay. So, now let us go for this size factor as a 0.85 and surface factor as a 0.85. Now, in this case we are right here assuming following datas. Okay. Following datas. Now, sigma en. So, now let us go for sigma en equal to, so 1 by 2 times of sigma u. Already you know the ratio. So, how we can calculate the value of sigma en if it is subjected to the tensile stresses. Okay. Now, we can just look out in data handbook. Okay. So, let us go for sigma en equal to half of sigma u. Okay. Now, you calculate how much you got here. So, now 1 by 2 570, whether it is a 225, 30, 35, it is a 285.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. Now let us substitute all values here. Now let us substitute all values. Now sigma En due to bending, okay, sigma equivalent due to bending, right. Sigma m, it is 8.25, right, into 10 to the power of 6 divided by d cube, right, plus sigma y is how much? Sigma y is 420. Okay, sigma En is 285. Okay. Now kf you took it as a 1. Sigma a is 2.75 into 10 to the power of 6. Okay, divided by d cube. Let us substitute value of a here, 1, b equal to 0.85. Sorry, right. Now we calculate what is the sigma equivalent because of bending. So someone find out. ಕ್ಯಾಲ್ಸಿಯಂ ಕೂತಿರಲ್ಲ ಎಲ್ಲರೂ ಏನು ಸುಮ್ಮಂಗ ಬರ್ಕೊಳಕತ್ತಿರೋ.
So 1.38 into 10 raised to 7.
1.38
into 10 raised to 7.
right. So let us notify this as equation number 1. Okay. Next. So next we consider the variation of axial load. Okay. So now, okay, equivalent axial load. Okay. So considering variable axial load, right. Now, so you calculate what is the minimum axial stress. Minimum axial stress. Okay. So now this is what a sigma minimum equal to. You can write a here, sigma a minimum. F minimum divided by area. Okay. So F minimum is 4 into 10 to the power of 3. Area is what? 5 by 4 d square. Okay. So you will get equation 16 into 10 to the power of 3 divided by pi d square. Right. Now similarly, maximum axial stress. Okay. So this is what F max divided by area. So F max is 10 into 10 to the power of 3 divided by pi by 4 d square. So we will get 40 into 10 to the power of 3 divided by a d square. Okay. Now let us calculate the equivalent stress here. Equivalent stress, not equivalent load. Equivalent stress. Okay. Equivalent axial stress. Now let us go for sigma EQ A equal to, okay, it is again same, sigma m plus sigma y by sigma En into kT plus sigma a divided by ABC. Okay. Now, as you got the value of sigma max, sigma minimum, find out sigma m and sigma a. find out sigma m and sigma a. So now let us go for the mean axial stress. Mean axial stress. Okay. So now this is what sigma max plus sigma minimum divided by 2. I think we are going to get 56 means 28 into 10 to the power of 3 divided by pi d square. Okay. Next, variable or amplitude stress. Variable or amplitude stress. Now sigma a equal to how much it is, 40 minus 16, it's 24 divided by 2. I think you are going to get 12 into 10 to the power of 3 divided by pi d square. Okay. Now we calculate here. So now in this case the load factor A, you can take it as a 0.7, okay, because it is a axial load, okay. So let us assume so sigma En equal to, again it is what, sigma u by 2 or 1 by 2 into sigma u. You refer design data handbook, you notify the equation number. Okay. So next we will go for load factor A equal to 0.7. 0.7 as noted from data handbook. Okay. So if the axial load is variable, you can select from 0.72. So let us check it in data handbook. Okay, so for reverse axial load you can take value of 0.721. Okay, let us go for 0.7 here. Let us go for 0.7. So keep the value of B and C same as that of earlier, 0.85, 0.85, right? Because size factor and surface factor remains the same. You can't change for axial load and you can't change for bending. Okay. So the same component is there. It has the same value of size factor and same value of surface factor. Okay. Now, so you know we can substitute all values in this equation to find out how much. Now, you substitute sigma m is 28 into 10 to the power of 3 divided by pi d square, right, plus sigma y is 420, sigma En is 285, right, into 1, sigma a is 12 into 10 to the power of 3 divided by d square. A is 0.7, B is 0.85 and C is also 0.85. You will get value in terms of d square here. You will get value in terms of d square. How much you got?
20.04 into 10 raised to 3 divided by d square.
Pardon?
20.04 into 10 raised to 3, sir.
Okay, so 20.04 into 10 raised to 3. Is it right?
Yes, sir.
Okay. Now, as the both cases are of tensile nature, okay, because of bending you are going to get a tensile stress, okay. Because of axial also you are going to get a tensile stress, okay. Now the total equivalent stress here, okay, the total or the resultant equivalent stress, okay. Now this is what sigma eq equal to sigma eq n b plus sigma eq n a, right. Now sigma eq n is what? This is the equivalent tensile stress because of bending moment. This is equivalent tensile stress because of axial loads. Now this has to be equated to the equivalent load or equivalent stress of the component, okay. That is what the design stress of the component. So what is the design stress or allowable stress is sigma y divided by n, sigma y divided by n. Now let us substitute here. Now this is what 1.387 into 10 to the power of 7 divided by d cube, correct, plus this is 20.02 into 10 to the power of 3, it is a d square, okay. Now this is equal to sigma y is 420, FOS is 2. Now we calculate diameter d. Now we calculate diameter d.
$41.19.
How much?
41.19.
41.19. So now you go for higher value, 42 mm. Now this is what the diameter shaft required. This is what diameter shaft required. So everyone solved? Everyone solved?
Yes, sir.
Okay, note the next one. A solid steel shaft is subjected to a bending moment that fluctuates between 600 Newton meter to minus 200 Newton meter, and at the same time the torque on the shaft varies between 420 Newton meter to 420 Newton meter clockwise, okay. This is what clockwise, to 210 Newton meter counterclockwise. 210 Newton counterclockwise. So, take sigma u equal to 500 megapascal, sigma y equal to 360 megapascal, okay, and design factor equal to 2. Neglect stress concentration effects, neglect stress concentration effect. Okay. So, in this case you need to consider Kf equal to 1, Kf equal to 1, right. Now, in this case you need to find out what is the equivalent shear stress, because it is subjected to the fluctuating torque, it is subjected to fluctuating torque. So, now let us note on given data here. Let us note on given data. Okay. So, maximum bending moment is 600 Newton meter, right. Minimum bending moment is minus 200 Newton meter, okay. And at the same time, so let us go for the shear stress, which is going to act in clockwise as a positive and counterclockwise as a negative, okay. So, T max, it is a 420 Newton meter, okay, and at T minimum, okay, it is minus 210 Newton meter, okay. So, sigma u is given, it is 500 megapascal, and the sigma y is given, this is 360 megapascal, and FO is equal to 2, FO is equal to 2. Now, you go for solution here, okay. So, now this is a shaft, okay, which is subjected to bending moment M max as well as M minimum, okay. Along with this one, it is also subject to the torques T max and T minimum, okay, T max and T minimum, okay. So, T max is here, T minimum is here. So, M max, M minimum, right. Now, again it is subjected to two type of loads. One is what, a bending load. So, let us take A equal to 1 here, okay. So, for torsional load you can take A equal to 0.7 and assume B equal to 0.85 and C equal to 0.85, okay. So, you must clearly specify, assuming, as the data is not given, you say assuming. So, A equal to 1 for bending load and A equal to 0.7 for torsional load, and B equal to 0.85 size factor and C equal to 0.85, and KTF or KF equal to 1, as they have clearly specified, neglect stress concentration effect, okay, right. So, you solve this problem, okay. One more thing is that one of your friend has said how to analyze the stresses for the crank, okay, for the crank. So, now I will draw the diagram here. You solve yourself this problem, okay. Now, we will draw the diagram. now this is what a crank. Okay, I have drawn side view here. This has to be straight, not in curve. Okay. Now the load is applied here. Load is applied here. So now they have given this is a fixation point. Okay. Let us take this as a section as a xx. Okay. Now we need to find out what is the diameter of shaft required here. Okay. You need to find out what is the diameter of shaft required. Right now. So if you consider in a plane of front view, let us take I will say this as a side view. Okay. So I will take this as a front view. I think now it is going to make it more clear. Now if you fix here, okay, if you fix here, now the load is acting at this point. Is it right? Load is acting at this point. Now what happens? So this load try to bend this entire section here, not only this portion, because it is fixed here. Now in this case it does not have any degrees of freedom here. Okay. Now what happens? This try to bend in the deflected manner here. Now we will draw the deflected position here. Now try to bend in this way. Okay. Are you agree with this one? Okay. So now because of this one, what happens? It is subjected to bending stress. It is subjected to bending stress. Okay. Now coming to the side view. Coming to the side view. So now this is what the fixed position of your shaft. Okay. Now load is acting here. Load is acting at a certain radial distance. Certain radial distance. Okay. So now this is what try to twist. Okay. This R in this way. Right. Try to twist this R in this way. So now because of this one, what happens? This is subjected to twisting moment. It is subjected to twisting moment. As section is subjected to twisting moment, what happens? It is subjected to shear stress. Okay. It is subjected to shear stress. Now in this case it is subjected to bending stress. Now how to get the bending stress here? Now this is what the support. Okay. Let us have we have a distance here LB. Now this is what R. Now we need to find out T here. T equal to what? P into R. So here you need to find out M. M equal to what? So P into LB. Now sigma B equal to what? M by Z here. So now in this case tau equal to T by ZB. Is it clear? So the person who has asked, are you attending class or
Yes,
not?
sir. Yes, sir. Yes, sir.
Okay, now you give the attendance. Just to give the attendance in chat box. So those who have given attendance can leave the class. ಕ್ಲಾಸ್ ಸರ್ ಕ್ಲಾಸ್ ಆಯಿತು. ಕ್ಲಾಸ್ ಮುಗಿಸಿ ಸರ್. ಏನು? ಹ್ಞೂ ಹ್ಞೂ